I wanted to work through an example that involves images of objects that are formed by curved mirrors. Remember, there's convex mirrors. They diverge light. There's concave mirrors. They converge light rays. This problem actually involves a concave mirror. Anyway, in this question, we're told that the Queen of England sits in front of a concave mirror, that's a converging mirror, and sees her image at 18 centimeters from the mirror. So that's one piece of information. We're told where the Queen is sitting, where the object is. We're told where the Queen sees the image. That's where the image is. We're then asked, how close should the Queen sit to see a upright, double-sized image of herself? So this is a problem that we're going to have to solve in two steps. The first step that we'll work on is actually to solve for the focal length of the concave mirror. The focal length is sort of the personality of mirrors. It describes how much they converge or how much they diverge. So we want to know the focal length of the Queen's mirror. And we can do that based on this first piece of information, that her image is 18 centimeters from the mirror when she's sitting at 1.52 meters from the mirror. Once we got the focal length, then we can solve the problem of how close should the Queen sit if she wants to see herself double-sized and upright. We can solve that problem for the Queen. So let's go ahead with this. Firstly, let's find the focal length, this personality of the mirror. The two pieces of information that we know are the object distance, so that's 152 centimeters, and the image distance, and that was 18 centimeters. And the object, the Queen, is in front of the mirror, so that's a positive object distance, P. And the image of the Queen, we're told, is also in front of the mirror, so that's a positive image distance, Q. From this information, we can use the mirror equation that relates the object, image, positions, and the focal length to solve for the focal length. So let me write that down. 1 over the focal length, or the inverse of the focal length, is the sum of the inverses of the object and the image distances. So often we see this equation written this way, where the inverse, the focal length, is the sum of the inverses of the object image distances. Sometimes it's handy to rewrite this equation by making a common denominator of the two terms on the right-hand side here. So a common denominator would be PQ. And if I make the common denominator for the first term, PQ, I've got to multiply it by Q. And if I make the common denominator for the second term, PQ, I've got to multiply it by P. That's just another way of writing the relationship between the focal length and the image object distances. But if we take that equation and we invert the left-hand side and the right-hand side, we get a handy equation for the focal length. It will be P times Q over P plus Q. And then we can just fill in the numbers. So I've got 152 centimeters. I'll skip writing in the units. Shouldn't really do that, but I will for time. I've got 18 centimeters. And then I've got the sum of the image and object distances. And that one I can do in my head. That's 170. And this whole thing will have it's got units of centimeters in the squared in the numerator. It's got units of centimeters in the denominator. So overall, it has units of centimeters. And if I multiply and divide, I've worked this out, 16.1 centimeters plus 16.1 centimeters. And so that's the focal length of the mirror. And note it is positive, and we were told it's concave, and that's consistent. Concave mirrors have a positive focal length. It's often very useful, very helpful to make a sketch drawing of the image formation to check your calculation. So I just want to draw a quick sketch of the formation of the Queen's image for this image in object position and check it makes sense, check our calculation makes sense. So let's do some ray tracing here. Here's the optical axis, horizontal line. Here's the mirror. And then on here, I'm going to mark the focal length. I'm going to mark it here. And so the distance from the center of the mirror to the across is the focal length. And as you see, it's on the mirrored side of the mirror. It's on the positive side of the mirror because this is a concave mirror. Now the object is roughly 10 times further away from the mirror than the focal length. I can't quite draw 10 times further away, but somewhere over here. And so let's see if we can just construct the image formation for this object with this particular lens, this particular mirror, and see if it makes sense to us. So I'm going to draw a couple of rays. I'm not going to draw, we talked in class, there's 4 rays that you can draw. There's one that strikes the center of the mirror and reflects back. There's one that travels in parallel to the optical axis, heads back through the focal length. There's one that travels in through the focal length, heads back parallel to the optical axis. And there's one that passes through the radius of curvature and travels back through the radius of curvature. It's a little difficult for me to draw all of these on this picture. So I'm just going to draw a couple just to check that my calculation was right. So let's try one that heads in parallel to the optical axis. And this ray is going to emerge through the focal point. So that's one ray that we can draw. A second ray that we can draw, I mentioned, is one that heads through the radius of curvature and will head back through the radius of curvature. So the radius of curvature is twice the focal length. So it's somewhere here. So we've got another ray, heads in something like this, and then heads in and heads back in the same direction. And so that's a second ray. A third ray that we could draw is that one, for example, that strikes the center of the mirror. And then whatever angle above the optical axis it strikes the mirror, it heads away from the optical axis with that angle. So that's a third ray. These rays, you can see, are converging at a particular point as they emerge from the mirror after being reflected by the mirror. So let me mark the image. The image is here, and that we see that the image is a little further away from the mirror than the focal length of the mirror. And that's what the question said, 18 centimeters for the image distance and 16 centimeters for the focal length. We also see that the image is inverted. And we weren't told that the image is inverted in the question, but for this image in object distance with this focal length mirror, that image is inverted. Now we've found the focal length of the Queen's concave mirror. We can answer, which of course we would do, her question about where she should sit if she wants to see an image of herself that's double-sized. So let's go ahead and figure that out. So the question is now become, where should she sit? What's the object position? And the things that we now know are, well, one of them is the focal length. Let's just stress that. We know that's 16.1 centimeters. And secondly, we're told that she wants to be twice as big. And so the magnification is going to be 2. And we might remember at this point from the magnification equation that the magnification is the negative ratio of the image to object distance, minus Q over P. So with this information, we can now solve for where the Queen should sit. And again, we're going to use the mirror equation that relates the inverse of the focal length to the sum of the inverses of the image and object distances. And we're going to modify this equation because actually we know the relationship between the image distance and the object distance because the magnification is 2. Now, I don't know yet the actual image distance or the actual object distance, but I know the ratio, the negative ratio of Q to P is 2. And so what I'm going to do is replace Q in this equation. I'm going to replace Q as being equal to minus 2P. That's just from the fact that the magnification is 2. And if I combine these two fractions here, I've got a 1 over P, and then I've got it's like a minus a half of 1 over P. I'm going to get 1 over 2P. So it's just rearranging, simplifying that equation. And then I can just take the inverses of the left-hand side and the right-hand side here to get the location that the Queen should sit at, the object position, the object distance. And that's going to come out to be the focal length divided by 2. And the focal length is 16.1 centimeters. So this is going to be 8.05 centimeters. And so that's where the Queen should sit, right up close to the mirror, to see herself twice as big as she actually is. Let's make a little sketch to check this result too. This relationship between these two image positions, the image and object positions, and the magnification. So I'm going to draw an optical axis here. I'm going to draw the mirror here, concave mirror here. I'm going to mark the focal length. Now, I'm changing the scale here from the first diagram because now the Queen's moved close up to the mirror. So we want to work close into the mirror. And in this case, we figured that the Queen should sit halfway between the mirror and the focal length. So the Queen's sitting here. And then we're going to go back and draw these various rays that we can. So one ray is this ray that heads in parallel to the optical axis, and it undergoes reflection, and it gets reflected back through the focal length. A second ray that we can draw is the one that heads towards the center of the mirror. And then whatever angle it is above the optical axis, as it approaches the mirror, it gets reflected at that angle below the mirror as it emerges from the mirror. And then another ray that we could draw, let's this time maybe draw a different ray, is one that heads into the mirror as if it's coming from the focal length and then gets reflected from the mirror parallel to the optical axis. So we've got a ray that comes in towards the mirror as if it's coming from the focal point or the focal length over here, something like this, and then it's reflected back parallel to the optical axis. So our eye is now seeing these different rays, the green ray, the red ray, and the magenta ray here. And it's reconstructing the apparent location that they come from. So let me just add some lines behind the mirror so that we can see that sort of reconstruction of the image by our eye and by our brain. So this ray upstairs here is coming out parallel to the optical axis. So it's reconstructed as coming from parallel to the optical axis. This ray in red here, it's reconstructed like this, and this ray over here, it's reconstructed like this. And these rays appear to merge at this location, approximately this location behind the mirror. And so this is where our brain reconstructs the image to be. And we see that this image is about twice as big as the object. So the Queen has indeed magnified herself to be twice as large, and it is upright. It's an upright, double-sized image. Anyway, I wanted to work through an example involving a curved mirror. This one was a concave mirror. Concave mirrors converge light rays. Concave mirrors are perhaps more interesting than convex mirrors in the sense that they allow for both magnification and minification. They allow for both upright and inverted images. And we saw that here. We saw that the original position of the Queen, she had shrunk herself. The final position of the Queen, she had magnified herself. And she had gone from being inverted to upright. Anyway, we used the mirror equation, we used the magnification equation to work our way through the problem. We used ray diagrams, ray drawings, to help us to confirm our results.